sklearncrossdecompositionPLSCanonical. Description: PLS-canonical is a method for canonical correlation analysis, which seeks to find linear combinations of two sets of variables that are maximally correlated. It is a supervised learning technique that can be used for dimensionality reduction, feature selection, and prediction. Inputs: X a 2D array of shape n samples. N features X representing the first set of variables. Y a 2D array of shape n samples. N features Y representing the second set of variables. Outputs: X weights a 2D array of shape n features X. N components representing the weights for the linear combinations of the first set of variables. Y weights a 2D array of shape n features Y. N components representing the weights for the linear combinations of the second set of variables. X scores a 2D array of shape n samples. N components representing the scores for the first set of variables. Y scores a 2D array of shape n samples. N components representing the scores for the second set of variables. Steps: calculate the covariance matrices of X and Y. Calculate the correlation matrix of X and Y. Find the eigenvectors and eigenvalues of the correlation matrix. The eigenvectors with the largest eigenvalues represent the canonical variates, which are the linear combinations of X and Y that are maximally correlated. The weights for the canonical variates are the X weights and Y weights. The scores for the canonical variates are the X scores and Y scores. Metrics: canonical correlations, the correlations between the canonical variates. These values measure the strength of the relationship between the two sets of variables. Explained variance, the proportion of variance in each set of variables that is explained by K. Canonical variates. Visualization plots. Scatter plots of the canonical variates. These plots can be used to visualize the relationship between the two sets of variables. Loadings plots. These plots show the weights for the canonical variates, which can be used to identify the variables that are most important for each canonical variate. Fine-tune parameters. N components, the number of canonical variates to extract. Scale, whether to scale the data before performing the analysis. Copy, whether to copy the data before performing the analysis. Uncertainty methods. Bootstrapping. This method can be used to estimate the uncertainty in the canonical correlations. And loadings. Challenges and fixes. Challenge 1: the data may be highly correlated, leading to unstable results. Sample use case that resulted in challenge 1: a dataset with multiple highly correlated features. Fixes to challenge 1. Use a regularization technique, such as ridge regression. Select a smaller number of components. Challenge 2: the data may be nonlinear, which can lead to poor performance. Sample use case that resulted in challenge 2: a dataset with a nonlinear relationship between two sets of variables. Fixes to challenge 2. Use a nonlinear method, such as kernel canonical correlation analysis. Apply a nonlinear transformation to the data before performing the analysis.